Welcome back to our discussion on the finite difference method applied to partial differential equations. Today our attention turns to utilizing this method for solving boundary value problems with a particular emphasis on addressing the Laplacian equation under specific boundary conditions. Let's delve into how the finite difference method provides solutions in this context. Join me as we begin exploring the complexities of numerical techniques for differential equations. Let's start the journey. Here we are going to discuss about the finite difference method for the boundary value problems in two dimensions. The finite difference method for 2D boundary value problems involves discretizing the domain into grid, approximating partial differential equations with the finite differences, and solving resulting difference equations with the boundary conditions. It is widely used in physics and engineering for problems like heat transfer, fluid dynamics, and electromagnetism, offering a numerical approach for solving complex differential equations in various applications. Here are the few steps involved to apply the finite difference method scheme: and discretize the domain, then finite difference approximation, construction of a difference equation, boundary conditions, then we need to apply the solutions of the difference equations. After that, post-processing and convergence and accuracy analysis. Here we want to solve the Laplace equation in rectangular domain, which is 0 to Lx by 0 to Ly with the Dirichlet boundary condition, del 2u upon del x square plus del 2u upon del y square is equal to 0 in the rectangular domain. And this is the left boundary condition, this is the right boundary condition. We both are equal to 0 for 0 less than or equal to y less than or equal to Ly. This is the below boundary condition and this is the above boundary condition. Okay, and these are also both equal to 0 for 0 less than or equal to x less than or equal to Lx. Now to apply the finite difference method, we need to discretize the domain into the grid point xi, yj, where xi is equal to I plus delta j and yj is equal to j plus delta y. Use the central difference approximation, the Laplacian, for the Laplacian and derive the finite difference equation at each interior grid point. So del 2u upon del x square will be approximate to ui plus 1 j minus 2 uij plus ui minus 1 j upon del x square, and similarly del 2u upon del x square will be equal to uij plus 1 minus 2 uij plus uij minus 1 upon del y square. And then after we need to apply the Dirichlet boundary conditions at the boundary grid point. After substituting these approximations into the Laplacian equation and rearrange to obtain the finite difference equation at each interior grid point, we have the relation uij is equal to 1 by 4 ui plus 1 j ui minus 1 j uij plus 1 and uij minus 1, which is given in equation number 1, which shows that the value of u at any interior mesh point is the average of its value at neighboring point to the left, right, above and below. The above equation is called standard 5-point formula. Also sometimes a similar formula is used, which is given by uij is equal to 1 by 4 ui minus 1 j plus 1 ui plus 1 j minus 1 ui plus 1 j plus 1 and ui minus 1 j minus 1. This is called the diagonal 5-point formula, and these both formulas can be expressed in the rectangle, and now we will discuss here both the schemes. One is the standard 5-point scheme and the diagonal 5-point scheme. Both can be easily expressed by this grid points. This is the uij, which we need to obtain if its neighboring points are given. For the first scheme, which is standard 5-point scheme, if we note this point is the left of uij and this is right of uij, this is the top of uij and this is the below of uij, then uij will be equal to the mean of these 4 points, which is left plus r plus b and plus t. Again, if we join the diagonal in this way and in this direction, this is the first point, this is the second point, this is the third point, this is the fourth point. Then uij is the mean of these 4 points, which is 1 plus 2 plus 3 and plus 4. So both the result which are discussed in the previous, both the scheme, standard 5-point scheme and as well as diagonal 5-point scheme can be easily expressed by using this grid scheme. Now in this diagram, if these are the boundary points and these are known points. Suppose that this is U1, U2, U3, U4, U5, U6, U7 and U8. We can easily get this point, and either we will use the standard 5-point scheme or the diagonal 5-point scheme. By using one of them, we can easily get the value of this point, and this will be equal to the mean of either by using this point standard 5-point scheme. So in that case we have is U2 plus U4 plus U6 and plus U8. If you are using to get this central point diagonal scheme, then this will be given by 1/4. We have is U1 plus U3 plus U5 and plus U7. This point is 7, U7. So one of them we can easily use to get the central point if its neighboring points are known. Now here we extend the same scheme, and these are the boundary point, and if the boundary points are known, then we can easily get all the interior point. And first we need to discuss here how we can get all the interior point of this grid scheme. So here you can see this is the most central point. First we need to compute this point by using one of the scheme. Suppose that this is U1, this is U2, this is U3 and this point is U4. So by using this standard 5-point scheme, we can easily get this point, which is the mean of these 4 points. After getting this point, we can now able to get to the other points. If we choose this diagonal point, we can compute this value, and by using this diagonal point, we are able to compute this in this point. Okay. Similarly, by using the same, we are now able to get the value of this point where the diagonals are intersecting. This point is known, all these corner points are known, and we can compute this value. Similarly, by using this diagonal, we are able to get this value. Similarly, now we can compute this point. We can compute this point as the neighboring points are known. We can compute this point and we can compute this point. So this is the complete process to get the values of the interior points if the boundary values or the boundary points are known in the grid. And the most important thing is that we need to improve these values corresponding to each grid point. This is very crucial, and our approach, which is finite scheme, will be very helpful to get these values and to improve the results. Now this is the solution process to apply to get the solutions. First we need to initialize the grid with the boundary conditions, then iterate through interior grid point using the finite difference equation until convergence. Then after compute the solution u xy at each grid point. In each case, the method is repeated till the difference between two consecutive iterate become negligible. The Jacobi method is also very helpful to improve these values, denoting the nth iterative of uij by unij. The iterative formula is reduced to as in equation number 3. This will improve the values of uij at the interior mesh point and is called the point Jacobi's formula. Gauss-Seidel method is also, again, we have the iterative method and can be represented as in equation number 4. This also will improve the interior mesh point and is called the Gauss-Seidel method. So by using one of these two methods, we can improve all the values of uij corresponding to the interior mesh points. In the previous part, we discussed how to discretize the rectangular domain to get the node points, and using the finite difference, we can compute the desired value at this point, and then we can improve the results. The accuracy of the result depends upon the step size between grid. The step size is as much small, we have more accurate result. Here we have the Laplacian equation, the same example, but the values of Lx and Ly, which are the domain for x as well as the domain of y. The Lx and Ly will be equal to 1, and now we need to choose the parameters. Lx is equal to 1. This is the length of the domain in x direction. Ly is equal to 1. This is the domain in y direction. So here we have, this is the x direction and one is y direction, and length of each we have is 1, and in the vertical also we have is 1. Nx is equal to 100. Initially we are taking here the nx is 5. We will do for nx is equal to 5, and ny is also equal to 5. This is 1, 2, 3, 4 and 5. Index is 1, 2, 3, 4 and 5. Similarly on y axis we have this is 1, 2, 3, 4 and this is 5. Here the 5 is equal to nx, and here is 5 is equal to ny, and dx will be equal to Lx minus Lx upon nx minus 1. This is dx. The step size we have is dx, and the number of these segment are 5, so will be equal to nx minus 1. So the dx will be equal to Lx upon nx minus 1, and dy will be equal to Lx upon ny minus 1. And the number of iterations we are choosing here 10,000, and tolerance we have is 1e minus 6. This is the convergence tolerance. Now we need to initialize the grid and the boundary conditions, and for that we need to generate the zero matrix. The size of the zero matrix will be according to the grid which we divide according to our desire. So here the nx and ny, these are the grid point on x-axis and for the vertical line. So here suppose that we choose 5.1, 2, 3, 4 and 5, and on the vertical line we have is 1, 2, 3, 4 and 5. The step size between these will remain same. So when we want to apply the bottom boundary condition, so here is, this is the bottom boundary condition, this for these values, and you can see that the index at this point will be y is equal to 1. Index for y is equal to 1, and x vary from 1 to 5. That's why for all the values of x we are using at this place colon, and the value at this x-axis we have is 0, but index is 1. That's why we have u colon comma 1 is equal to 0 at the top point. Here the boundary condition, top boundary condition u x ly. Okay, so here we have is ly, and the values will vary from 0 to 5. That's why we are using colon for x to pass all the values, and the value of y we have is fixed at this point, which is ny. So for this boundary condition we have u colon ny is equal to 0. Now for the left boundary condition, and on the left boundary condition we know that the value on this y axis x is 0, u0 y is equal to 0. Okay, and for the x equal to 0, the index we have is 1. That's why u1 colon is equal to 0, and similarly for the right boundary condition, here the value of y will vary from 1 to 5. 1 to 5 are the index. Okay, and here the right end point we have is nx, which is used for x and will remain constant, but the value of y will vary from this point to this point according to the index. So we are using colon at this place, and which is the right boundary condition corresponding to this one. Now here we have this formula is very important, and on the basis of this statement we can compute all the desired value, and we will improve the values by using Gauss-Seidel iterative solver. Okay, so first we need to compute all the values corresponding to the node point which we have divided according to the above discussion, and you can see that this equation is used to compute the values at the interior grid points, okay, which is 1.4 ui plus 1j plus ui minus 1j plus ui j plus 1 plus ui j minus 1. On the right hand side, all these are the old value, and after computing all these we get the new value. So on the left hand side we have is the new value, and all these are the old values. Okay, so by using these old value we need to compute, or we need to get the new value of uij. So let's discuss here how we can implement this code. Here you can see at the place of 1v4 we have is 0.25. This is u I plus j I plus 1 comma j, then u I minus 1 j, u I j plus 1, then u I j minus 1. So all these are the four neighboring points corresponding to uij, and this is the new one. Now what we do, we have to initialize the loop for these grid points only for the interior. Okay, as you know, we divide this grid on 1 to 5. Okay, and this is the these are the boundary points, and 5 is equal to nx. This point will be nx minus 1. So we need to compute only this point 2 to nx minus 1. So the loop for I as well as loop for j both will run from first we are applying here the loop for I 2 to nx minus 1, and this will be end at this place. Then after we will apply the loop for j. Okay, and that will also remain in the same way. This point and this point, this is 1 and this is 5. These are the interior point, and only at this interior point we need to compute the values. Okay, so here this is the ny, and this point is ny minus 1, and this is 2. So the loop will work for 2 to ny minus 1. Okay, so by using this sequence of statement, we are able to compute all the interior points where the grids are intersecting. Okay, and you know all these values will be computed, and the value will be stored at this place, which is u, and u will be at this place. Now the important thing is that we need to improve all these values, and for that we are using at this place iteration, which will start to initialize at this place iteration from 1 to maximum iteration. Okay, which is assigned we have is 10,000, and this loop will end at this place. Okay, so the values which are computed at this place will be stored at this place, and again this will be used at this place, and for the first iteration, for the second iteration, the value will pass at this place, and we will compute, and the value of u will be updated, and this will go to at this place. So this loop will work until this condition is justified, which is the convergence, and if this condition is justified, the tolerance between the two consecutive iteration, this is the old value and this is the new value, absolute value of these two maximum must be less than tolerance. Okay, so when this value is less than tolerance, then the loop will break and will return the result. So in this way, this loop will work for the improving the results, which is based on Gauss-Seidel iterative solver. Okay, so here are the, after computing all the values corresponding to the x, y and u dash, we need to plot the solution now. Okay, so for that we need to generate mesh grid for 0 to Lx as well as 0 to Ly, so that we can fix according to that for the three-dimensional plot. Okay, so we are generating here surface. This is the x, y, which are obtained from this place. These are the values of u, and we are taking at this place u transpose, so that the dimensions of these will same. And after that, we need to use here X label, Y label, Z label. This is the title, box on, grid on. So all these are the same statement which we have already discussed in the previous lecture, as well as we have organized some special session to plot the 2D and 3D graph. So I think this is not much typical, only these are the labels and to plot the graph. Here these two statements will display the number of iterations count and as well as the maximum number of difference. So this will print the number of iteration, how many iterations are used, and this will print the difference or the error between the two consecutive iterations. Now we can easily execute all the sequence of statement, and when we will further execute this sequence of statement, our program is ready. Just we need to press at this place, and when you will press, you can see that the number of iterations for these values we have is 1, and the maximum difference between two consecutive is 0. Okay, and now also in the graph you can see, again execute this sequence of statement, and you can see that in the graph the grids are we have is 5 point on the corresponding to x-axis, and that of y also we have is the 5, and all these grid lines are intersecting, and by using the boundary points we have the interior points and we have the result. And also if you want to check all these values in the workspace, you can verify here. This is the, you can check the values of u, double click on it. So these are the grid and the values of each are 0, and the size is 5 by 5. Now if you want to increase the number of grid we are taking at this place is 100, and these are also we are choosing 100, and again execute this statement, and now the graph is appeared in this form. Okay, now the thing is the left boundary and right boundary in each cases these were 0, but now if we manipulate these values, suppose that the top boundary condition is at this place we have is 1, then execute this sequence of statement. The graph which will appear now at this place we will have is in this way. And if you want to rotate this graph in 360 rotation, you can do like in this way. You can check it. If you are making some more changes, suppose that the top boundary condition is 1, and that of right boundary condition is also 1, and then execute the sequence statement, we have this diagram. And if you want to rotate these values, we can check this graph by rotating in any direction. Yes, so this is the actual graph by changing these values, and you can check these value. This is the 1, and at this place also we have is 1, and on this side and at this side these are 0. So in this way you can easily manipulate all these values, and corresponding to this value, if you want to check the values which are computed at this place, and you see that the size of each we have is 100 by 100 for the u and u old, x and y. So this is very important. The size of each we must have equal, only then the graph will be plotted. If you want to check the values which are computed in this we have, yeah, so at the top you can see that the values, all the values are 0, and that of on the left side we have are also 0. But as soon as you will scroll down and check here, the values are equal to 1 according to our assignment, and then go to right hand side, these are also 1. Okay, so these are the boundary conditions, left, right, top and bottom, and these are the interior point which are computed by using this finite difference scheme. Okay, so now you can manipulate all these values for the different domain, different points, and the process which we discuss here is very quite simple. Now in the you can choose different more several examples to apply this finite difference scheme for the boundary value problems. So in this way, using Jacobi's iteration alongside the finite difference method in MATLAB offers a methodical strategy to approximate solutions within the predefined tolerance level. The iterative procedure continuously updates the grid points by considering neighboring values until the solution converges, thereby ensuring accuracy. The iterative procedure continuously updates grid point by considering neighboring values until the solution converges, thereby ensuring accuracy. Convergence is assessed by monitoring the solution's change, and this method adaptability to different grid sizes and boundary conditions enhance its utility across various computational physics and engineering applications. Additionally, to deepen your understanding, we have provided additional examples through uploaded script files, presentations, and PDF document. Thank you for your active participation in the lecture till the end.